Good afternoon, everyone. Thanks for joining our session today. This is the second session on thermography that we are jointly conducting with Conrad. Our first session covering the fundamentals of thermography can be found on the www.conrad.biz webpage. If you didn't get to attend the previous session, please feel free to access the recording on the website. My name is Jason, and I am the EMEA Business Development Manager from Keysight Technologies, previously known as the Electronic Measurement Group within Agilent Technologies. I'm based in the UK, covering much of EMEA. I will share my contact details at the end of today's session. So after today's session, should you like to discuss any of these points I talked about further, please feel free to get in touch. You can send an email to me, or you can send an email to Sabrina. As the title of today's webinar suggests, our topic today seeks to help us dispel some myths around thermography, as well as discuss some opportunities to maximize our usage with thermal cameras in order that you get the best analysis from them. As thermal cameras become more affordable, the area of thermography is attracting a lot of interest from people across a wide spectrum of industries. But before that, let me give you a short introduction to Agilent, to Keysight. Keysight Technologies is based in Santa Rosa, California, the US, with 9,600 employees across the world. We have facilities across the world with our primary R&D and manufacturing sites located in various locations in the US, in Malaysia, Japan, and China. With a revenue of close to $3 billion, we are listed on the New York Stock Exchange under the symbol KEYS. I thought it would be interesting to give us a brief insight into the history of Keysight Technologies. We trace our history to the founders of Hewlett-Packard way back to 1939. Back then, HB started off with test and measurement instruments, and as you all know, today is a well-known player in the technology sector. In 1999, the test and measurement business of HB was spun off to become Agilent Technologies, and Agilent promptly became the world's premier measurement company. However, just fairly recently, in November 1st last year, less than a year ago, the electronic measurement business became an independent company, 100% focused in electronic measurement, and that company is called Keysight Technologies. Today, we are a market leader in electronic measurement, providing solutions across a wide array of industries, in communications, in industrial, semiconductor, computers, as well as aerospace, defense. Without further ado, let me get down to today's main agenda, which I trust you will all find both beneficial as well as interesting. There will be three parts to today's session. In the first part, we will be discussing some common myths and facts around thermography. While thermography is a technology that makes analysis much easier, it isn't always just a matter of point and shoot, nor does a thermal camera a powerful do-it-all instrument. Although I must say that with the correct technique, one is able to really do a lot with a thermal camera. It is because of a lack of basic understanding around thermography that gives rise to some common myths or misconceptions around the area of thermography. Now, this part will seek to debunk some of these myths and clarify what works and what doesn't with a thermal camera. The second part, we will look at two different approaches to thermography, either qualitatively or quantitatively. Undoubtedly, the majority of users use a thermal camera to make a qualitative or relative analysis. However, for those that want to have a more accurate analysis done, often need to ensure that some measures are taken to compensate for various effects, such as reflection of the surface that is being analyzed, or even the effects from the object's surrounding environment. In the third part, we will uncover some interesting applications in thermography, and the whole idea of this is to spur you to think about how you may use a thermal imager in your very own setting. So let's begin looking a little bit more into these. So today, thermography is being adopted across a wide array of industries. Needless to say, one of the most important applications today is in the area of predictive maintenance in the industrial sector. And this covers electrical and mechanical inspections by people such as technicians, engineers, consultants. In fact, some larger companies even employ 100% full-time thermographers just to perform thermography at their sites. Thermography is used to inspect areas such as bearing, wear and tear, cracks in refractory materials, to check for levels in water tanks, as well as accumulations within those level tanks, as well as temperature distribution across a wide array of objects such as paper mills, PCB boards, etc. Another area that's really growing in terms of adoption of thermography is in the area of building maintenance. Here, we encounter people who use thermography in air tightness inspection, something that's really relevant and becoming even more relevant across Europe to assess energy efficiency and to look for heat loss through leaks in a building structure. Also inspection in areas of ventilation, air conditioning, as well as floor heating, for example. The other area that many of us are very familiar with is the area of electronics, as well as some R&D applications, whereby we find that thermal cameras are really very useful in determining the thermal profile of a board assembly being evaluated, as well as in the validation process of a prototype board that a company has just designed. Of course, there's a lot of talk today about applications in health, research and development, whereby thermal cameras are used in really new areas such as the detection of injuries in athletes, even in animals. And today we hear of thermography being used in the area of archaeology, for example. So a lot of interesting applications with thermography. So let's very quickly dive into part one. As mentioned, myths around thermography are often due to misunderstanding on how thermography works. And today I hope to be able to cover the top 10 misconceptions today that we have gathered based on the interactions that we have had with people who have been using thermal cameras or who plan to use thermal cameras. The first myth says that thermal images can see through walls and even clothing. This is something that we need to debunk because thankfully this is really not the case. A thermal camera is not an X-ray machine, so you can be assured that your privacy is quite safe. Now the basis for this is that thermal cameras detect the infrared emission from the first molecular level of a particular surface, and this is important. Now this means that if you are scanning a particular object, what you are scanning is the infrared emission from the surface and not necessarily what is behind or below that surface. As such, when you scan a wall of a house, you are probably not going to see if there is anyone behind that wall. These surface energy levels can, however, be affected by the environment or even operational conditions, heat transfer processes, and material characteristics. However, when there is an object with a different energy level behind that surface being analyzed, that energy may transfer through conduction to that surface, and you might still see a difference at that portion of the surface. One example, just to illustrate this further, if one were to hide a gun behind a shirt, the thermal camera might still be able to detect the presence of the gun, as the energy transferred from the gun might be transferred to the surface of the shirt and subsequently affect the energy being radiated at the area in contact with the gun. So that's an example with a gun. Another example is a common example, such as a wall. With ordinary visual inspection, the wall looks uniform. However, with a thermal camera, one could possibly start to see construction details of the wall, especially with reference to insulation, or sometimes give an indication of the wall itself. If there are problems with the wall, if there is a missing insulation, the thermal camera really is very useful in these kinds of situations. So typically with at least a 10 degrees stable difference in temperature between the outside air and the conditioned environment inside the building, a thermal camera is able to detect missing or damaged insulation, or even give an indication of how the insulation was installed. Here is an example of how adhesives are used in installing the wall panels in my office show when I use my thermal camera. And this is an image of my actual office. If I were to make a scan, I would be able to see not just the wall, but really how the adhesives were used in the installation of the insulation levels of the wall. So as you can see from this example, a thermal camera is really a very interesting and useful tool in the analysis of buildings, walls, and other living space. But that is another huge topic altogether, which we probably need to cover separately. Going on to myth number 2. A few weeks ago, I was making a scan with my thermal camera together with some colleagues, and as the room wasn't very bright, the person next to me took out a flashlight to shine on the object I was scanning, with the assumption that I was going to get a better scan with more visual light. It is sometimes almost intuitive to think that we need some light to get a better thermal image. In reality, that is not the case. Since thermal cameras detect not visual light but infrared radiation, no visual light is actually necessary in order to make a thermal scan. This simply means that thermal imaging is possible even in total darkness. Now, this is quite different from night vision cameras. Night vision cameras work on the basis of light amplification. This means that some light, even though very little, needs to be present in order for night vision cameras to work. And this light could be present in the form of ambient light or as an additional light source that the night vision camera provides. Now, for thermal cameras, this is not a problem. Infrared radiation happens when an object is above 0 Kelvin. As objects around us are all above 0 Kelvin, we can be assured that there is an infrared radiation from every surface around us. 0 Kelvin on Earth here is just a theoretical value, which means that every surface that you scan with a thermal camera, you would be able to get some form of infrared radiation detected by the camera. So whether or not there is any visual light, the thermal camera is still able to function very, very well. Moving on to myth 3, which is an interesting one. Does color affect emissivity? Do I need a dark surface in order to have more accurate temperature readings? In reality, not necessarily so. There are many factors that affect emissivity. Among them is the type of surface. Assuming two of the same surface type is scanned, factors such as if the surface is smooth or rough, if it is polished or not, if it has been painted over with a layer of paint or varnish, these factors can really affect reflection and the emissivity of the surface, and will subsequently affect the readings on your camera. Generally, colors do not make a difference. However, it can have a small impact if there is a higher carbon content in the paint or the coloring that is used on the surface. Now let's look at this a little bit more closely. Here is an example of a metallic mug with 5 different types of tape pasted on its surface, each with its own color. And as you can see here, you got blue, turquoise, red, black. Now they look different visually. However, when I make a thermal scan of this, all 5 different colored tape shows up almost the same in the IR image. And this goes to show how very clearly how little color has an impact on emissivity. Now, for those of you who are really sharp, you would have noticed that I mentioned 5 different types of tape, which is what we are seeing on the thermal image. However, on the image on the left, it doesn't really show 5, it shows 4. This is simply because the 5th one at the top of the 4 visible tape, as you can see over there, is actually a transparent cellophane tape. So again, you can see the color isn't showing any large impact on the IR emission. Moving on to myth number 4, and this is something that I get from many people. I need to look for red spots on my thermal image to identify the warmest areas. That means the warmest spots are always represented by red or even white on the thermal image. In reality, that's not really the case. Often there is a tendency to equate red or white as the hotter spots in your thermal image. Now, while thermal camera manufacturers try to accommodate this intuition by adjusting their color palettes so that red and white are indeed often an indication of warmer temperatures, colors on the thermal image only serve to give meaning to energy levels. What we actually want to see in a thermal camera is a contrast of colors as opposed to type of colors. So it is the color contrast or the differences that reflect the different energy levels of the surface being scanned and not the type of color. Various color palettes are given as options in thermal cameras so that users can select the one that is most suited to their eye or the situation. In fact, it is worth noting that sometimes a monochrome color palette is more useful than a multicolored one, because if you are making analysis on a surface with smaller temperature variations, a monochrome color palette really brings out the different energy levels that your eye is able to capture as compared to a multicolored color palette. Now again, I must remind you that the fundamentals of thermography are covered by a separate session, and this session, if you have any further questions on the fundamentals, I would really encourage you to access the previous recording to have a clearer understanding of the fundamentals, so that some of these things that I'm sharing today would be more meaningful to you. Moving on to myth number 5, I need to ensure that I get all my settings on the camera right when making a scan, or else my scans will be inaccurate. Now this next point is quite important. In daily practice, we often just get a few seconds to make a scan, and if this is true, this might really be a problem. In reality, this is not necessarily true. Ideally, we want to ensure that we have as much correct settings or parameters input into the camera prior to performing scans. But sometimes time is really a factor. As such, instrument software is very important to help users to make that additional fine-tuning, such as changing the emissivity level, the reflected temperature, ambient temperature, selecting a different color palette once the user is back in the office. Here I would like to take the opportunity to show how a good software is able to help us compensate for these challenges. So I'm just going to minimize that and open up software. And just to use an example of a very useful software, and this is a software from Keysight Technologies that comes with our U5855 thermal camera. It is downloadable for free. In case you're interested, you can just go to keysight.com and download the software and try it out yourself. And once I've downloaded the image into the software, a good software will always allow you to make modifications in the basic parameters of the image that you have captured, such as emissivity, reflected temperature, ambient temperature, humidity levels, and distance. This is really very important. Sometimes while you're in front of the object, you might not necessarily know for sure the nature of the surface that you are making a scan on. As such, sometimes it's really helpful to be able to make corrections to your emissivity value, your emissivity settings once you are back in the office. Another area that a good software will also help you in performing analysis is the ability to change the span and the levels of the image. And as you can see over here, a software should ideally allow you to very easily and conveniently make adjustments to your span and level. Earlier on, I mentioned about color palettes. A software would also allow you to change the color palette according to what suits best for you. Also, for the software that we have, one is also able to set an alarm so that only areas that are above or below a certain temperature shows up as a color image. Okay. One of the things that really helps with the software is to be able to determine temperature levels, temperature points at any area within the diagram. And over here, I'm just dropping points across the thermal image over here. And this is something that's really very useful, and this is something that can only be done if your camera captures images as radiometric images. Now, radiometric images are basically images that contain a data point behind every pixel in this image. And as you can see, with an image that is radiometric, one is able to just drop any point and you'll be able to get a data point. So if the camera that you have does not save radiometric images, this is one benefit that you will not be able to have. Besides that, also a good software will also enable you to have a basic analysis tool. And over here, I'm just drawing a line across the image with this analysis tool. And if I go down here, I'll be able to see the line profile of the image. And this is really a very, very useful tool for you to see how the temperature change across a particular area that you are making a scan on. Okay, so that's very useful. And of course, you will have max and minimum temperature indications over there. Okay, I'm just going to remove everything over here to make this a little bit cleaner. Okay, so once we have all these images, it's also important for us to be able to share the findings with our colleagues of our analysis. So over here, there is a function for us in order to generate a report very easily, for us to attach an image, key in some basic information, and subsequently just export it. And I'm just going to write down test over here as an example. Okay, and I'm generating a report. And here is an example of how easy it is to create a report. And this is the type of software functions that you generally want to have with your thermal camera. So over here in this example, very specifically, it tells me the date, the time, as well as the settings on my camera. And as you can see over here, the resolution of the image, temperature range, as well as various analysis tools that I have deployed on the image. All right, I thought this was quite useful for us. And I should go back to the slides. Okay, now while good software is really very useful, this is an important note to make. Software will not help to correct unclear IR images that was taken on site. Now, we know that the fundamentals of thermography is that we need to make sure that your images are focused correctly. Your images are clear and as sharp as possible. Now, if we do not get that right, the software will not be able to make such corrections. We need to get the right focus and the right composition when capturing the image. And without this being done on the camera, there will be a huge risk that your temperature readings and your subsequent analysis will not be accurate. So software is very useful, but the fundamentals of thermography, which is snapping a sharp image, must always be maintained. Now, myth number 6 says that thermography can be carried out anytime, anywhere, without any concern, as long as my object has high emissivity. That's not all that true. In reality, when making scans outdoors, effects such as wind, precipitation, sun, or even common atmospheric conditions such as dust or particles can affect the results and possibly give a false indication on hot spots or cold spots. That's why it is really advisable for us to plan our scan activities so that these factors do not affect our readings. Now, let's talk about the sunny day. We all love a sunny day. However, on a sunny day, we need to exercise extra caution to avoid reflections from the sun when making a scan outdoors. Now, with a bright sun on a cloudless day, this can contribute significantly to reflective energy on the image being scanned if one is not careful. Now, how about rainy days? On rainy days instead, we have the risk of humidity and moisture that can really affect the accuracy of your readings. Thermal cameras detect humidity well, so this is one area to be extra careful about. So besides, between a very sunny day or a rainy day, I would recommend a cloudy day to make an outdoor thermal inspection. But do remember to be sensitive to wind that might bring about heat transfer from convection. So in conclusion, if there is a need to make an outdoor measurement, try to keep these in mind. Shield your target from the wind on windy days, or even make an inspection at night or early in the morning where there is no bright direct sun. Also, change your viewing angle to avoid reflections from the sun. Moving on to myth number 7, and it says that everything is all right as long as I have my emissivity tape. Now, if you remember in the fundamentals of thermography, we recommend the use of emissivity tape as a measure to overcome surfaces that we do not know its emissivity. So by setting the 0.95 emissivity setting, and this is a typical setting we set for these kind of tapes, I can know that my readings are accurate. Now, in reality, this is not always true. Now, having a black or emissivity tape is convenient, but under certain circumstances, it cannot be used due to safety reasons, such as when an object is far away or when an object is very hot. So, for example, making a scan on industrial transformers is usually not going to allow you to paste any electrical tape, as they are usually fenced up or caged up due to safety or legal reasons. Or if the scan is being made on a printed circuit board assembly with multiple components, it will also be quite difficult to use emissivity tape to cover all the surfaces. Now, in the event that emissivity tape cannot be used and one needs to make an accurate temperature measurement, keep these in mind. Firstly, correct the emissivity setting with the help of an emissivity table. We know that emissivity tables, you can easily Google it. Also, adjust the setting of your camera with other atmospheric parameters. And we shall go through some of these in the second part later on. Now, the other way around this is to coat your object with high emissivity paint. This is a special paint that will give you a uniform emissivity across all surfaces of the object. So, of course, you only use this if you're allowed to use this paint or this spray on the object, as it usually can't be removed. This is a method that is really useful when making a scan on a prototype board, for example, in the electronics industry, as the emissivity paint can be sprayed across all the surfaces on the board, and it will subsequently give an even emissivity value across all components on the PCB. Okay, let's look at myth number 8. The closer I am to the object, the more accurate my measurement is. In reality, it really depends on the object. The next point, this point is to clarify about the distance from the object that is being measured and how it impacts our thermal scan. Many work on the assumption that the closer one is to the object, the higher the accuracy of the temperature measurement. There is a little bit of relevance to that statement. To obtain accurate temperature measurement, spot size needs to be considered. Spot size on the camera needs to be smaller than the target area, and this is very logical. If it is larger than the object, the temperature measurement will not be accurate. However, the real benefit of being closer to the object is actually the ability to capture more resolution with a shorter distance. This is very similar to taking a picture with a digital camera. The closer you are, the more detail and resolution you capture in that image. I think it's worth for us to ask, what is the shortest distance possible? This is really important if you are making a scan on the PCB assembly where you want to see heating on individual components or PCB tracks. And this largely depends on the instrument you are using. Every thermal camera specifies the minimum distance allowed by which the accuracy is guaranteed. In the market today, most cameras state this as between 20 to 50 centimeters. I thought it is worth noting that the Keysight U5845A allows close-up scans of up to 10 centimeters. Who really finds this useful? This is really useful for people who are making a scan on an object that has a lot of details, such as in a printed circuit assembly. So I think it would also be good at this point to visualize the effect of distance on our measurement. When it comes to thermal cameras, one commonly used term is the IFOV, that stands for instantaneous field of view. Now, the instantaneous field of view refers to the smaller size of an object the camera can see or resolve. In this illustration, this is represented by the red dot. As the camera is further from the object, the IFOV becomes larger. So in this example, we see that at 10 centimeters from the object, the IFOV is showing a size of 0.31 millimeters. But as the camera is brought further away from the object, the IFOV eventually increases to 31 millimeters at 10 meters away. And this really shows how we compromise on resolution the further away we get from the object. Myth number 9 says that the term resolution always refers to the same thing in data sheets of any thermal camera. Now, while they often enough refer to the native resolution of the detector of the camera, some manufacturers have other kinds of resolution specification that require us to be careful in order not to get confused by them. And here are just a few examples. IR resolution, this is where we have thermography data with every pixel. This is what we call as a radiometric image, as what I mentioned earlier on with the software. That is, every pixel carries a data point of the temperature data of that particular pixel. Very useful for analysis. The second type of resolution is called image resolution, where no measurement data is necessarily included in the image. Which brings me to a point that when selecting a thermal camera, try to get one that gives you images that are radiometric. Every pixel on that image, whereby every pixel on the image would contain a temperature data. Then there's a third kind of resolution which is called a visible image resolution, and this refers to the resolution on the visible image that is generated by the camera from the scan. And finally is the display resolution of the thermal camera, and this refers to the instrument's display resolution itself. So as I have boxed up in red over there, the most important is IR resolution that carries temperature data. The higher the IR resolution, the more temperature data you get. Now, some thermal camera manufacturers specify the perceived enhanced resolution from some sort of fusion technology. Just a point to note that this does not necessarily translate to radiometric information. So when selecting a new camera, make sure that you have radiometric images from your camera. So a U5855A has a fine resolution capability that improves the resolution by 4 times through a complex built-in algorithm. This is a technology that we call using fine resolution, and in these images that are produced from the camera are all radiometric. Just a point to note. Now, the final myth today says that thermal cameras today are really affordable, even as low as 500 euros. Now, that is quite true. Firstly, one needs to differentiate between an imaging IR thermometer and an actual thermal camera. An IR thermometer only captures the temperature of a specific spot, while thermal cameras give an overall surface temperature of the entire surface of your object. So you've got to be very careful on what you are purchasing. Are you measuring just one point, or are you making a spatial measurement of the entire surface? However, over the years, prices of thermal cameras have indeed significantly dropped. What used to be priced at 10,000 euros today costs much less. My tip for you is for us to choose a thermal camera that is most suitable for your application. And the points to consider when selecting a thermal camera would, number one, of course, be the resolution. Most serious thermographers today go for a resolution of at least 160 by 120 pixels to 320 by 240 pixels. Consider the sensitivity and accuracy. What is the smallest temperature difference do you expect to see in the object that you are scanning? Is it 0.01, 0.07 degrees? Consider this when you select the camera. Temperature range, what is the highest temperature that you anticipate at the areas that you plan to scan? Is 120 enough? 350? These are really important because if you, for example, purchase a camera that is just has a maximum reading temperature of 350 degrees, and you find that you need a higher temperature measurement capability, then it might be a limiting factor for you, and you might need to purchase a new camera. Also consider whether or not you require a manual or fixed focus. My advice is always to use a manual focus camera, because fixed focus cameras do not allow you to have control over the image that you are scanning. In order to get a sharp image from the image that you're scanning, you need to physically adjust your own location, whereas a manual focus camera would allow you to adjust the focus of your image just as you would with a DSLR digital camera. All right, and as we know that if we do not have our focus done correctly, this will impact the accuracy of our readings. Finally, the last point to consider is, of course, your budget. Get a camera that meets your need, but also fits your budget. Sometimes it is worth doing that little extra to look beyond the banner specs in order to evaluate what is the best solution for you. Moving on to the second part on qualitative versus quantitative thermography. I hope that you have found the 10 myths that I went through interesting. There are, of course, many more of such myths. And if you have questions, feel free to contact me to discuss some of your specific questions. When it comes to qualitative or quantitative thermography, how different are they and what extra steps need to be taken. So when it comes to thermography, there are generally two approaches. The first approach is the one used by most, that is a qualitative analysis. This is when the need isn't to make an accurate measurement, but instead to identify potential problem areas. The thermal camera here functions to just point a user to areas to focus on for further analysis further down the road. So this could be in the form of from a PCBA to a larger industrial transformer. So what's important with qualitative analysis is to make a relative analysis on a relative difference on various spots in the area that you are scanning. Now the second approach is when we need to make a quantitative analysis. Here is when measurements need to be as accurate as possible. When it comes to making these kinds of quantitative analysis, there are really several factors that need to be considered in order to ensure that you get the most accurate readings possible. So chief among them is, of course, the emissivity of the surface or the point that you want to make a measurement on. That is really very fundamental. There are also other factors that need to be considered, such as reflectivity, i.e. how much of infrared that you are reading is actually a reflection from its surroundings. Even transmissivity, and this is a bit rare, but something to be considered for certain circumstances. In reality, most objects are opaque in the IR world, and transmissivity can be considered 0. However, when it comes to assessing transmissivity, there are certain objects that allow some transmissivity to happen, such as an IR mirror, or even an everyday object such as a plastic bag from your supermarket. If you were to make a scan on this plastic bag, you will see that it has a transmissive nature. And of course, the emissivity, as I mentioned earlier on, this is really very fundamental. If we do not get the emissivity settings right, really our readings, our scan will not be reliable. So let's look at a little bit more into quantitative analysis. When making a quantitative analysis, one needs to consider 3 types of possible compensation in order to have as accurate analysis as possible, in order to get the most accurate temperature readings from your camera. They are firstly reflective compensation, where one needs to consider the possible IR energy reflection from the objects surrounding it. Secondly, we need to consider ambient compensation, such as humidity, ambient temperature, or even distance from the object. This might be something to seriously consider if the measurement you are taking is being done in winter, or if there is a large difference between what you are measuring from where you are and from where you are making that measurement. And finally, as I mentioned, that little rare condition whereby transmissivity compensation needs to be factored in. But even before that, remember that the first step to take is to ensure that you have focused your image correctly. This is where having a manual or autofocus camera is really useful to ensure that you get the most focused image regardless of your position. One of the most fundamental aspects in thermography is to assess if the hotspot you are seeing is actually a real hotspot from the object, or if it is a perceived hotspot as a result of the reflection from objects surrounding it. So in order to do this, here's a tip. Real hotspots don't move or change while reflections do. So with a thermal camera, move to the right or to the left. If this is a reflected hotspot, you will notice that these thermal cameras will move with you. If it doesn't, it is likely a genuine hotspot. But remember, ensure that you have your emissivity setting set correctly. So that's really fundamental. Now, next, determine the thermal energy in your surroundings or background. We do this by turning around and scanning the area around the targeted object, and then estimating the average temperature. You may also use references to room temperature if you are indoors, and that is often readily available. Alternatively, crumple or crinkle a piece of aluminum foil, flatten it on a piece of cardboard, and here you may just use a cardboard from your cereal box. Then fan the foil plus cardboard around the surrounding area of the object and place it in between your camera and target. Subsequently, scan the aluminum surface. Now, we are all, looking into the emissivity table, we can tell that aluminum has a very low emissivity value. Hence, the aluminum surface will act like a diffuse reflector, and it will give you quite a good idea of reflected temperature around the object you are scanning. Once you have deduced the reflective temperature, input this parameter into your camera. And here I am assuming that your camera gives you this flexibility to make these adjustments. So, in selecting your camera, make sure that your camera, besides giving you free software, besides meeting your basic banner spec requirements such as temperature and resolution, also see if your camera is able to allow you to input reflected temperature settings, as well as other correction parameters that we will cover in today's session. The next area that we need to compensate is what we call as ambient compensation. Here's where we accommodate differences in ambient or atmospheric temperature. The distance and humidity or any gases in the atmosphere, for that matter, have the potential to attenuate IR radiation from an object. Hence, making the necessary adjustments to the settings of your camera can really help to compensate for these variables. This is just like reflectivity. These adjustments are really important when your target has low emissivity. So, obviously, if your target has very high emissivity, if you're not too far from the object and you're under normal room conditions, these factors are not so important. But when you are in more challenging situations where the emissivity is low, in areas where the humidity is very high, these compensation needs to be considered in order to increase your accuracy to as much as possible. So if you are making a scan in the winter, for example, or your environment that you're in is indoors and you are scanning through an opening in a window to a location outside, try to put in the right parameters in terms of object distance, as well as whatever information that you can get regarding the humidity of the environment. And usually you can get these types of information from available sources such as a remote outdoor thermometer. And finally, some users have installed a special type of window called an infrared window. And you might have already noticed that ordinary glass window behave as an IR mirror. Infrared window instead is used to separate two differing pressure temperatures within an area, while allowing an infrared energy at a specific wavelength to pass through it. So this is like a special kind of glass that allows infrared to be transmitted through it. But it is very important when making these type of compensations to know what is the transmission rate of the window or the glass that is being used. This is where you need to contact the supplier of that glass to get this information, and this should be input into your thermal camera. All right, moving on to part 3, some common applications in thermography. And as I mentioned, the whole idea behind this is to trigger us to think about how we may use a thermal camera in our very own settings. Now, a common thermography application today is in the area of solar panels. Solar energy has been an interesting area for people in many countries across Europe, and this is really seen in the many solar farms that have sprung up across many countries here, especially in Western Europe. Now, a solar PV system consists of several main components. Number one would be solar panels to absorb and convert the solar power to electricity. Secondly would be an inverter to change the electrical current from DC to AC. And finally, the mounting and cabling accessories that make up the system. Now, because a solar panel consists of a matrix of solar cells, sometimes identifying a failed cell can be quite a challenge. The failure of any solar cell may lead to a drop in power generation, causing output yield losses. So a solar farm may have up to a few thousand solar panels, and really testing each individual solar panel at the installation site using a direct wire connection can be really very time consuming and cumbersome. And a more effective method today is using thermography to quickly scan and detect if solar cells are overheating due to shading or defective cells. So when the cell is shaded or if the cell is defective, the cell will consume power from the adjacent series of solar cells instead of generating power. Now this will cause the cell to overheat, and as you can see from the image over here, the cells that are defective really show up very clearly on the thermal scan. And this is really where the benefit of using a thermal camera comes in, whereby a user is able to very quickly scan across the entire panel and very effectively point out defective cells. Now, another area where thermography is increasingly being adopted is in the area of electronics. So historically, characterizing an electronic device was a combination of understanding the design or just guessing where the hotspots could potentially be. Then subsequently, after best guessing the hotspots, an engineer would then place temperature probes at those points, and using a DAQ, for example, data acquisition, to measure temperature across the various configurations and plot out the external temperature profiles. However, this exposes you to errors in design and not being able to capture them until it is too late. If, for example, you do not make a good enough best guess, or if you're just not making the right connections at the right areas to capture hotspots. Now, with thermal cameras, you can really test and visualize hotspots before you do a longer-term data acquisition. If you use a thermal camera to create a thermal profile, you can very quickly see where the hotspots are. However, you do need a line of sight, though, to get an accurate location of where your trouble areas might be. Thermal cameras in this kind of applications can provide faster and better insight into making temperature measurements, as it has the ability to measure temperature distribution over the entire circuit board and to measure it very quickly. As such, no hotspots will go undetected. All right. So this is really useful if you need to make temperature logging across a prototype board, for example, as it can very quickly help you isolate problematic areas, and subsequently you can very efficiently use your data logger to log in more detail at those problematic areas using actual contact measurement points. And this really saves you a lot of time and effort as compared to how it was used to be done without a thermal camera. Another example would be electrical and mechanical systems that need to be inspected, and this is something that is done very regularly at any building facility. So shown here is an IR image, and next to it is its respective visible image of an electrical system in a typical manufacturing plant. And as I mentioned, you see this in most buildings, in any facility. An IR thermography inspection generally runs at specific time intervals. This is something that you need to do as part of your preventive maintenance program. And for this example, you can see that hotspots really show up very quickly and very easily. And generally, this is a very clear indication that there could be a problem with connection, or this could be a case of an unbalanced load in this application, for example. So typically, manufacturers who design something would put their prototype designs and and even select samples from their manufacturing lines for rigorous burn-in tests to ensure that it meets specified quality. And this also goes for UPS manufacturers, industrial UPS, that's what I'm referring to here. Industrial UPS generally needs to have a burn-in test, and this is how the industrial UPS looks if you've not seen one before. Here is where using a thermal camera is extremely useful in helping us to identify problem areas that might show up as hotspots in these UPS. As you can see, there are many connection points in an industrial UPS, and without a thermal camera, it will be very, very troublesome and very time-consuming to make measurements at each and individual spot. So with that covered, I would just very quickly like to use a few minutes to just talk a little bit about the U5855A True IR Thermal Imager from Keysight Technologies. This instrument is the latest addition to our family of handheld instruments. It comes with a detector resolution of 160 by 120 pixels, but it also comes with a built-in algorithm that enables us to have images with a resolution of 320 by 240 pixels. And that is actually effectively giving us 4 times more resolution with this built-in algorithm. We call this technology fine resolution technology, and the whole idea behind this is to allow users to have a higher level of resolution at the price of 160 by 120 pixel price point. This instrument also has a thermal sensitivity of 0.07 degrees, which is really very sensitive, to ensure that even small temperature differences are detected. Now, this camera was designed with the user in mind, therefore ergonomics is a prominent feature of this instrument. This is really something quite interesting because traditionally thermal cameras tend to be large and bulky, and especially if you're using a thermal camera for prolonged periods of time, having an instrument that is ergonomic is really very, very helpful. So let me just give you an idea of how the fine resolution that I mentioned about, how does it really benefit the user in actual terms. So here's an example of the result of a Keysight's True IR technology compared to an ordinary 160 by 120 detector camera. The one on your left is a typical 160 by 120 resolution camera. As you can see, the sharp edges look quite blurry. However, with fine resolution that is embedded in our camera, one is able to get up to 320 by 240 pixels, and it is shown here in the image on your right. So this is not just something that is that we talk about, but something that can be clearly seen from the images that are being captured by the camera. So in ensuring ergonomics, the instrument is rated IP54, that is water and dust resistant. It works for both right and left-handed users due to its adjustable strap. It also comes with 11 languages user interface. Worth to note is how well spaced the buttons are so that they're easy to access. The camera comes with a standard 3-year warranty, just like all Keysight instruments, and there is a currently there's a promotion that is being run that gives additional 2 years warranty. This means that users are assured 5 years of worry-free usage of the camera. So earlier on I mentioned about the well-spaced out buttons, and this is really the main benefit of this is the ease of use in adjusting the span and the level of the thermal image, simply because of the joystick mechanism that we have over here that allows you to very quickly move it to the right, left, top and bottom to make adjustments to your image so that you get the best contrast possible. The thermal camera also comes with image logging so that users can log images up to once every 7 seconds, as well as several viewing options such as IR image, visible image, as well as 2 kinds of fusion images such as a picture-in-picture or blend images. I mentioned about the 5-year warranty. This is just for your information. So besides thermal cameras, Keysight also offers a wide range of other types of handhelds, such as multiple performance multiple handheld DMMs from low-end to high-performance handheld DMMs, insulation testers, clamp meters, even handheld scopes and LTR meters. And should you have any questions, please feel free to send a note to Sabrina Schmidt from Conrad, as well as to send an email to me directly if you have any questions. All right, then we've reached the top of the hour. Sabrina, I shall pass the line back to you.
Hi, Jason, thank you for the nice presentation. Now we have one question here from the attendees. The question is, where an ambient compensation can be done, in software or in Commodore?
Yeah, it can be done on your camera, and that's really something that's really very useful, because sometimes it helps to make corrections on the software. Sometimes it helps to make corrections on your camera. So for this particular setting, it can be very easily done on your camera. It can actually also be done on your software if you should require to.
Okay, thank you. Are there any questions more? In Tool there are no questions, but you can take it. Oh, Adam says, very interesting presentation. Thank you, Adam.
Thank you.
Okay. Jason?
All right.
Thank you for your presentation. Have a nice day.
Thank you, everyone.
Goodbye.
Bye.